In performing our day-to-day activities, we use various words like work, energy, and power, which are closely related to each other. And sometimes we use these words without paying much attention. In this chapter, we are going to learn about these concepts more carefully. People carry out various tasks in daily life like lifting of weights, carrying of weights, sweeping, cleaning of house, cooking of food, and watering of plants like this. These are all some of day-to-day activities. Similarly, people employ machines in their homes to carry out different tasks like blowing of air by fan, pumping of water by electric motor, heating of water by electric heater, etc. Washing machines, vacuum cleaners, cleaning of clothes, and cleaning of houses respectively. In all these things, we can observe that they need energy to do work. Generally, this energy is supplied to human beings through food and for machines through the electric energy. In all these examples mentioned above, we notice that a person or a machine doing work spends some energy to do work. For example, to lift your school bag, you spend some energy. Similarly, an electric fan uses some electrical energy for blowing air. In our daily life, we use the term work in various situations. But according to physics, the meaning of work is different. And now we discuss what is the scientific meaning of the work. A work is said to be done when a body displaced by a displacement S when a force is applied. Suppose you consider this. The body is at rest. A person is pushing the body to move. Still the body is at rest, even though he is spending some energy. According to physics, since there is no displacement, no work is done. In this case, the force is applied vertically down. Here also there is no displacement on the body. Here also no work. In this case, a body is lifted to height h. The body is displaced vertically by a displacement h. Here we can say the work is done. In this case, when force is applied, the body is displaced by a displacement s. Here also work is done. And mathematically, work done is the product of force and displacement. Again, force, which force we have to consider? Suppose we consider a force F is applied on a body making an angle theta with the horizontal, and the body makes displacement in horizontal direction. In this case, the complete force is not utilized to move the body along this direction. Therefore, we take work done is the product of force along this direction, that is force along displacement, into displacement. The force along this direction is nothing but the horizontal component of force, that is F cos theta. F cos theta into S. And work is nothing but the dot product of force and displacement. Since F is a vector, S is a vector, and Fs cos theta gives the dot product of F and S. Therefore, work done is the dot product of force and displacement. Work is a scalar quantity. The units of work are Newton meter or joule. The dimensions, it is force into displacement. For force it is m1 L1 t minus 2, and for displacement it is L. Now this is equal to m1 L2 t minus 2. If we consider force is 1 Newton, displacement is 1 meter, then we get work is 1 unit, that is 1 joule. That is, if a force of magnitude 1 Newton displaces an object by a displacement 1 meter, then work done is 1 joule. According to physics, work is said to be done when a body is displaced by a displacement S when a force is applied. To understand this concept, we take some more examples. Suppose we consider a porter carrying a box on his head and walking horizontally. In this case, what is work done against gravitational force? A gravitational force is acting vertically down. The displacement is in horizontal direction. The angle between these two components is 90 degrees. We know that work done is Fs cos theta, that is Fs cos 90, Since the value of cos 90 is 0, we get this is 0. Work done against the gravitational force is 0. Now the question is he not doing any work? Yes, he is doing work. But technically, the work done against the gravitational force in moving the body along horizontal direction is 0. But he is doing the work against the frictional force and he is spending some energy to maintain the position of that body. That we discuss later. In this case, the important thing we have to observe, work done by which force or work done against which force. This is very important while discussing work done. We take another example. A particle is moving along a circular path of radius r. Then you know what is work done by the centripetal force? At any point if we take, the centripetal force is acting towards the center. This is the direction of centripetal force and always the displacement direction is tangential to the circle. That is, it is perpendicular to the centripetal force. Here theta is 90, work done is Fs cos 90, you get it is 0. We take another case, when force and displacement are in the same direction, then theta is 0, work done is Fs cos 0, this is equal to F into S. In this case, work done is maximum. When force and displacement are in opposite direction, in this case, theta is equal to 180, cos 180 is minus 1, work done is Fs cos 180, this we get minus F into S, this is negative work. To understand this, we take one example. An object is in motion along a horizontal surface. Frictional force is acting opposite to the motion. In this case, the displacement and applied force, both are opposite in direction. Theta is 180. The work done by the frictional force is negative. Work done by the applied force is not negative. Both are in the same direction. But work done by the frictional force is negative since it is acting opposite to the motion of the body. Now we take another case. An object of mass m is lifted to a height h. In this case, work done by the gravitational force in lifting to height h. To lift this body, we have to apply a force which is equal to weight of the body, that is F equal to mg. It is acting vertically down. The displacement is h and theta. The angle between force and displacement is 180 degrees. Then we get work done is Fs cos theta, that is mgh into cos 180. This is equal to minus mgh. The work done by the gravitational force is negative. Then work done by the person, it is not negative. Why? Because he is applying the force in the direction of motion. Now we take this example. The work done to lift the body to height h is mgh. Now we consider an object is on an inclined plane. The plane is smooth, that is no friction is there. In this case also, the work done in moving the body to the top of the inclined plane, it is mgh. When the body is on this inclined surface, the weight of the body is acting vertically down, mg. This can be resolved into two components, mg cos theta and mg sin theta. Now this is the force which makes the body to slide down. To move this body, we have to apply a force which is equal to mg sin theta. If due to this force, we move the body along this length L, then work done is Fs cos theta, this is mg sin theta into L into cos 0. From this triangle we can write L sin theta equal to h. Therefore, this is equal to mgh. In the same problem, if we consider frictional forces there, then work done is greater compared to mgh. If the frictional force is there, the work done, this is force into displacement. The minimum force required to move this body is mg sin theta plus frictional force, that is mg sin theta plus mu k mg cos theta into L, which is not equal to mgh. Now we take another example. An object of mass 10 kg is on an horizontal surface. What is the work done to lift this to a height 1.5 meter? In this case, to lift this body, we have to apply a force which is equal to weight of the body, that is F equal to mg, and the displacement is the height what we lifted, that is 1.5 meter. We are applying the force in the direction of displacement. theta equal to 0. Therefore, work done is Fs cos theta, or this is equal to mgh. Now, work done is mass is 10. The value of g, that is acceleration due to gravity, is 9.8 meter per second square. 10 into 9.8 into 1.5 into cos theta is cos 0. This we get 147 joule. We take another problem. An object is rest on horizontal surface. A force of magnitude 10 Newton is applied, making an angle 30 degrees with the horizontal. If the body displaced by 10 meter horizontally, what is work done? What is given in our problem is an object is rest on horizontal surface. A 10 Newton force is applied, making an angle 30 degrees with the horizontal and displaces the body by 10 meter. Here work done is nothing but Fs cos theta. This theta is the angle between applied force and displacement. Force applied is 10 Newton, displacement is 10. Now this is equal to 10 into 10 into cos 30. Cos 30 is root 3 by 2 and this is equal to 100 into root 3 by 2. This we get 50 root 3 joule. Energy. Already we know that to do work, energy is required. What is energy? If you have energy, then only you can lift the body. If electrical energy is there, then only fan can rotate. If electrical energy is there, then only motor can work. In all these examples, we are observing that energy is the capacity of doing work. Simply, the capacity of doing work is called energy. And work and energy both have same units and dimensions. That is, the unit of energy in SI is joule and the dimensions are m1, L2, T minus 2. In nature, we can find energy in so many forms. Suppose we consider a man is lifting an object. Which kind of energy is using? Yes, mechanical energy or muscular energy. Water boiling. Because of heat energy, water boils. Fan is rotating. Due to rotation of fan, we get mechanical energy, but fan gives work because of electrical energy. The different forms of energies in nature: mechanical energy, heat energy, chemical energy, electrical energy, magnetic energy, light energy, sound energy, nuclear energy, wind energy, etc. We can convert one form of energy into another form, but we neither create nor destroy the energy. This is law of conservation of energy in nature. For example, if we consider electric fan is not creating any energy, just it is converting electric energy into mechanical energy. Steam engine, it converts heat energy into mechanical energy. What about car? Yes, fuel energy, that is chemical energy, is converted into mechanical energy. In thermal power station, heat energy is converted into electrical energy. At hydel power station, water energy is converted into electric energy. In windmill, wind energy is converted into mechanical and this converted into electrical energy. In case of solar cells, solar energy is converted into electric energy. That means we can convert energy from one form to another form. We cannot create nor destroy the energy. This is law of conservation of energy. The different sources of energy: sun is the main energy source on the earth, and wind, this is also energy source. Tides of sea, energy of water flow, petrol, coal, nuclear fuels, these are all different energy sources. In these energy sources, you can observe a difference. If we consider sun, wind, tides of sea, energy of flowing water, they never decrease in nature. But in case of petrol, coal, nuclear fuels, if you go on using these sources, the amount will decrease. And these kind of sources are called renewable energy sources, and these are non-renewable energy sources. These non-renewable energy sources we get from mines. If you go on use these sources, At some time, we won't get any further energy source. Therefore, using renewable energy sources are preferable compared to using of non-renewable energy sources. Now we discuss in detail about mechanical energy, energy of rotating fan, energy of a moving car, energy of stored water. All these are mechanical energies. We take a small example. Suppose if a marble is on a plate, take this marble to height h and allow it to fall. Then what happens? The plate will break. That means marble at some height, it is having energy. It can do some work. Similarly, this car is at rest. It is not having any energy. If the car is moving, yes, it can do work. The energy of this marble, the car, rotating fan, all these comes under mechanical energies. The energy of a machine, the energy of electric motor. We can classify mechanical energy as potential energy and kinetic energy. Potential energy means the energy possessed by a body due to its position. The object at height h, it is having some energy. This kind of energy is potential energy. Similarly, we consider a compressed spring. Yes, it can do some work. It is having energy. A compressed spring is having potential energy. Now we try to derive an expression for potential energy. Potential energy is nothing but the work done in creating the position of the object. The potential energy stored in a body is nothing but the work done to give that position for that body. That means if you do work on a body against a force, that will be stored in body in form of potential energy. If you lift an object to height h against the gravitational force, then body attains some energy which is called gravitational potential energy. Similarly, if you compress a spring, while compressing you have to do some work. That work will be stored in spring in form of potential energy. Now we try to derive the expression for potential energy of an object at height h. Your potential energy is nothing but a work done in lifting the body to height h. When body is lifted to height h, the work done against gravitational forces, the potential energy that stored at height h. The work done against the gravitational force is nothing but the potential energy stored in the body. Now to lift this body, we have to apply a force which is equal to weight of the body, that is mg. Displacement s is h. Both displacement and applied force are in the same direction. Theta is 0. The work done is Fs cos theta. This is mgh cos 0. This is equal to mgh. Therefore, the potential energy of the body at height h is mgh. Similarly, the potential energy of a compressed spring is nothing but work done in compressing the spring. When you compress a spring, you have to compress the spring against the restoring force. The restoring force of a spring is given by minus kx, where k is a proportionality constant which is called Spring's constant. Restoring force minus kx is acting along this direction. To compress the spring, you have to apply a force which is equal to kx. But in this case, the applied force depends on position. In previous case, the applied force does not depend on position. Suppose we consider this is initial point, that is x is 0. I am starting compressing the spring from this position. At this position, the restoring force is 0. When you go on compressing the spring, the restoring force increases. At this position, the restoring force at x equal to x, it is kx. Therefore, a force has to be taken as average force. In this case, average force is kx by 2. Therefore, work done, average force into displacement, kx by 2 into x, this is half kx square. Since here, force is continuous, it is not a constant thing. It is varying with displacement. We are taking average force. Therefore, work done in compressing the spring is half kx square. Potential energy stored in spring is nothing but half kx square. Another kind of mechanical energy is kinetic energy. The energy possessed by a body due to its motion is called kinetic energy. Here we can observe that when a fan is placed in a stationary water, it cannot rotate. But if it is placed in flowing water, it rotates. That means a flowing water is having a kind of energy that is kinetic energy. Another example, if a car is stationary, it is not having any kind of energy. When it is moving, yes, it is having energy. Energy possessed by a body due to its motion is called kinetic energy. The kinetic energy of a moving body, this is nothing but work done by a force to stop that body. If an object is moving with velocity v, to stop this what we have to do? We have to apply a force opposite to the motion of this body. The work done to stop this body is nothing but the kinetic energy of this object. Whatever the work done by the force is nothing but the kinetic energy of this object. Your work done is nothing but force into displacement. Further, force can be written as mass into acceleration. This we can write m into a into s, where m is mass, a is acceleration, and s is displacement. Now in this case, the initial velocity is v, final velocity, we are stopping the body, is 0. From equation v square minus u square, this is equal to 2as. We get minus v square is equal to 2as, or a equal to minus v square by 2s. This negative sign indicates the acceleration is opposite to the motion of the body. Since the force is applied in opposite direction to the motion, acceleration is also opposite direction. This is negative acceleration, which is called a retardation. Therefore, the work done is MAS, that is m into minus v square by 2s into s. This we get minus of mv square. This is the work done by the force to stop this body. This force is doing a work which is equal to half mv square. That means this body is having an energy of mv square, and this energy is called the kinetic energy of the body. Next we discuss about work energy theorem. Work done by an unbalanced force on an object is equal to change in its kinetic energy. Now we consider an object of mass m moving with velocity u. Due to application of a force F, it gains velocity v after displacement s. In this case, initial velocity is u, final velocity is v. Because of application of force, it gains acceleration. Because of application of force, the velocity changes from u to v. In this case, acceleration. This we can find using the formula v square minus u square equal to 2as. We get acceleration a equal to v square minus u square by 2s. Now the work done by this force is force into displacement m into a into s. Force is m into a and displacement is s. Substitute the value of acceleration. Thus we get m into v square minus u square by 2s into s. On simplification we get half mv square minus half mu square. Half mv square is nothing but final kinetic energy. Half mu square is the initial kinetic energy. That is, work done is kf minus ki. Work done is change in kinetic energy. Therefore, work done by an unbalanced force on an object is equal to change in its kinetic energy. Similarly, we can consider a work done is equal to change in potential energy. For example, if a body is lifted from the ground to height h, the work done is nothing but mgh. This is nothing but the change in potential energy of the body. On the ground, the potential energy of the body is 0. When it is lifted to height h, the potential energy is mgh. You take one more example. If a body is lifted from height h1 to height h2, in this case, the work done is nothing but the difference in potential energies between these 2 points. That is mgh2 minus mgh1. mgh2 is the potential energy at this point. mgh1 is the potential energy at this point. Now we take some problems related to the concept of work and energy. An object of mass 5 kg is lifted to a height 10 meter from a height 5 meter. What is the minimum force required to lift from 5 meters to 10 meter? Object is at a height 5 meter. At this position, the gravitational force is acting vertically down. To move this body vertically up, we have to apply a force which is equal to gravitational force. Therefore, the minimum force required to lift the body is weight of the body. Weight means m into g. Here mass is given as 5 kg. G is acceleration due to gravity, which is 9.8 meter per second square. Now this is equal to 5 into 9.8, 49 Newton. 5 into 9.8 Newton. This also can be written as 5 kg weight. Kg weight is another unit of force. 1 kg weight is equal to g Newton or 9.8 Newton. Now this we get 49 Newton. What is potential energy at height 5 meters? At height h, the potential energy is nothing but mgh. M is mass, g is acceleration due to gravity, h is height. Now in this problem, m is 5, g 9.8, h is 5 meter. Substituting these values, we get the potential energy at height 5 meters is 245 joule. What is potential energy at 10 meters? Using the same formula, taking h is equal to 10, we get potential energy at this position 5 into 9.8 into 10, 490 joule. Now what is work done to lift from 5 meter to 10 meter? Yeah, the work done to lift the body from 5 meters height to 10 meters is nothing but change in potential energy. At this position the potential energy is 490 joule, and at this position it is 245 joule. Now change in potential energy is 490 minus 245. This is equal to 245 joule. We take another problem. An object of mass 10 kg moving with velocity 5 meter per second. Its velocity changes to 10 meter per second after 5 meters. Now related to this, the first question is, what is initial kinetic energy? We know that the expression for kinetic energy is half mv square. M is mass and v is velocity. Initial velocity is 5 meters per second and mass is 10 kg. Now this is equal to 1 by 2 into 10 into 5 square. This we get 125 joule. What is final kinetic energy? The final kinetic energy of mv square. Here v is the final velocity. Now this is equal to 1 by 2 into 10 square. We get 500 joule. Now what is change in kinetic energy? Change in kinetic energy means final kinetic energy minus initial kinetic energy. This is 500 minus 125, 375 joule. What is work done by the applied force? According to work energy theorem, the work done by the applied force is nothing but change in kinetic energy. Therefore, work done is 375 joule. What is the magnitude of the applied force? We know that work done is force into displacement. In this problem, work done is 375 joule. Now, work done is force into displacement. 375 equal to F into 5, or F is 375 by 5, 75 Newton. A law of conservation of mechanical energy. This states that in an isolated system which is only subjected to conservative forces, the mechanical energy remains constant. That means there is no change in mechanical energy in a system where the conservative forces are acting. Already we discussed about what are conservative and what are non-conservative forces. According to law of conservation of mechanical energy, in a system, the energy may change from one form to another form, that is potential to kinetic or kinetic to potential. But the total mechanical energy of the system always remains constant. Let us verify the law of conservation of mechanical energy in case of a freely falling body. Consider an object of mass m is allowed to fall from height h. In this system, due to which force the ball is falling? Yes, because of gravitational force. Since the body is falling freely, our consideration is no other forces are acting, only the gravitational force is acting. And gravitational force is a conservative force. One, it is at height h. The velocity is 0. At this position, the object contains only potential energy. When it is moving towards the ground, since the height is decreasing and the velocity is increasing, the body gains kinetic energy and loses potential energy. If we take any point in its path, it contains both potential and kinetic energies. When it reaches the ground, since the height is 0, potential energy is 0 and it is having maximum kinetic energy. To verify law of conservation of mechanical energy in this case, we have to show that the total mechanical energy at any point during this path is constant. If we consider at A, at this position, body have only potential energy. This is nothing but mgh. Energy at A is mgh. We take this is equation 1. I am taking another point B, which is at a height h minus x from the ground. The distance between A to B is x. At this point, object have both potential and kinetic energies. Potential energy at this point is mg into h minus x and kinetic energy is half m vb square, where vb is velocity at this point. And for this path from A to B, using the equation v square minus u square equal to 2as. Here initial velocity is 0 and velocity at B is Vb. We can write Vb square minus 0 square is 2gx. From this you can write Vb square is 2gx. Now the kinetic energy at B is of mv square of m into 2gh. This is equal to mgx. Now the total mechanical energy at B is potential energy plus kinetic energy. This is mg into h minus x plus mgx, or this is equal to mgh. We take this is equation 2. When object is at C, it has only kinetic energy. Kinetic energy at C is half m vc square, where vc is velocity at C. For this path A to C, using equation v square minus u square equal to 2as. Initial velocity is 0, final velocity is vc. Substituting these values in this equation, we can write vc square equal to 2gh. Our kinetic energy at C is EC is half m vc square. This is equal to half into m into 2gh, or EC equal to mgh. We take this as equation 3. From equations 1, 2 and 3, energy at A is equal to energy at B is equal to energy at C. That means energy at any point, the total mechanical energy at any point is same. This verifies law of conservation of mechanical energy in case of a freely falling body. Now similarly, we try to verify law of conservation of energy in case of vertically projected body. Suppose we consider a body is projected vertically up with initial velocity u. At projection point, the initial velocity is u. The gravitational force is acting vertically down. That is, gravitational force opposes the motion. As it is moving up, the velocity decreases and height increases. That means, as it is moving up, kinetic energy decreases and potential energy increases. At ground, the object is having only kinetic energy. At some height x, it has both potential and kinetic energies. In this case, the body reaches the maximum height till its velocity becomes 0. Velocity is 0 means at this position the kinetic energy is 0. Object is having only potential energy. That means in this case, in case of vertically projected body, when it is projected, it has only kinetic energy. When it is moving, the kinetic energy is converting into potential energy. When it reaches the maximum height, all its kinetic energy converted into potential energy. Again from this position, it reverses its path. To verify law of conservation of mechanical energy in this case, we have to show that the energy at any point along this path is same. First we consider at projection point. Let us take this is point A. At this point, object has only kinetic energy and energy at A is half mu square. We take this is equation 1. Now at B the object is at height x and the velocity is decreased compared to A. At this point, the total mechanical energy is sum of kinetic and potential energies. Energy at B is kinetic energy plus potential energy. And kinetic energy at this point is half mvb square, where vb is velocity at B. If we take this path A to B using equation v square minus u square equal to 2as, we can find the value of vb. Here final velocity is vb, initial velocity is u. vb square minus u square, this is equal to minus 2gx. Here a is minus g, s is x. From this we can write vb square equal to u square minus 2gx. Therefore, the kinetic energy of mvb square is half m into u square minus 2gx, and potential energy is mgx, and total mechanical energy at B is the sum of potential and kinetic energies. This is equal to mgx plus half m into u square minus 2gx, or this is equal to mgx plus half mu square minus mgx, and we get energy at B is half mu square. We take this as equation 2. Now at point C, that is at maximum height, since velocity is 0, kinetic energy is 0, object has only potential energy. And potential energy at this point is mgh. For this path A to C, from equation v square minus u square equal to 2as, here this is initial position, initial velocity is u, and final velocity is 0, a is minus g, s is h. Substituting these values we get h is equal to u square by 2g. Therefore, energy at C is mgh. This is equal to mg into u square by 2g, or energy at C is half mu square. We consider this is equation 3. From equation 1, 2 and 3, it is clear that energy at A is equal to energy at B. This is equal to energy at C. The total mechanical energy at any point along this path is same. This verifies law of conservation of mechanical energy in case of vertically projected body.